All right, hey everyone. We're a minute or so, give people a chance to join, and then we'll get started. Okay, looks like we've got a good amount of folks coming in. So yeah, let's get started. Hey everybody, thanks for joining us today. I'm Julia. I'm a technical evangelist here at Tecton. I'm here with my teammate Sergio, and I'll let him introduce himself real quick.
Hi, I'm Sergio Farragut. I'm a developer advocate here at Tecton, and I'll be demoing how to build a fraud detection system for you today.
Awesome. Yeah, we're really excited. We're here to talk about, what it takes to build a real-time fraud detection at scale. And also, we'll show you, like Sergio said, some cool demos that might inspire you on how these systems can be built even better, improved even faster, all that good stuff. So I'm gonna share my screen and then we will get started. Okay, so here's a quick overview of what we'll cover today. I'm going to spend just a couple of minutes giving you some intro and context for what you'll see later in Sergio's demo, which is going to cover, some of the latest techniques for making fraud detection real time, making it highly accurate and scalable. And then we'll close out with a real world story featuring one of our customers, North. So that'll be cool. Oh, and we've got some exciting fraud roundtables coming up that you can be a part of. So stick around to hear about that at the end. Okay, so I wanted to start with, talking a little bit about what's going on in the world of fraud. Um, if you're in this space, you know that the threats are only growing in scale and complexity. They're getting more and more sophisticated. Financial institutions are reporting more fraud attempts. Fraud losses are increasingly a problem for businesses across lots of different industries, not just financial services. And fraudsters are now using AI to get even more creative and effective in their tactics. So what's really important technically about this is the requirements that it creates, right? So these fraud detection systems now need, a lot more fresh data from different sources in order to make, the best possible decisions. And they need those predictions or decisions to happen really, really quickly in the moment. So whether it's about, payment fraud, money laundering, anti-money laundering, account takeover, other forms of identity fraud, the list goes on, right? There's a lot of different fraud use cases, but the technical challenges are pretty similar across those. Because modern fraud detection isn't just about transactions. Of course, it's everywhere in the customer journey. If you think about all of the different touch points that you might have from account creation, logins, of course, transactions, but even like things like password resets, things like that. What makes fraud detection work in all of these different settings is having high quality, consistent data that combines both, your real-time signals with historical patterns, so models can have the best understanding of what's going on and act on that context. But the challenge in doing all of this at scale is, keeping the experience smooth for all of your legitimate customers, right? You want them to have a great customer experience, but while also catching fraud. And what's worked, in the past for these types of use cases might not work so well anymore, because of everything we just talked about. For instance, rule-based systems, they can make really fast decisions, but they need to be constantly updated as fraud patterns evolve. You could end up maintaining a ton of different, thousands of rules, and a lot of them could end up being less effective, as fraudsters learn how to get around them, right? And for batch ML, a lot of folks start out with this. It might work really well for identifying past patterns, but we're talking about real time here, right? And doing batch alone is really like bringing a stick to a sword fight. Like a purely reactionary approach will only get you so far. But then you have off the shelf. There's a lot of off the shelf options and solutions which can work really well for standard fraud scenarios. But as you probably know, fraud patterns can vary significantly across different businesses, depending on your specific company situation, your transaction patterns, your risk tolerance, et cetera. So this is why many teams end up building real-time ML systems themselves. They bring their systems in-house because they really want that control and flexibility. But building and operating a real-time ML system like this yourself, it opens up a whole new can of challenges, right? You need infrastructure to handle different data from different sources. So, your transaction systems, batch data from your warehouses and data lakes, real-time signals from external APIs that your systems are calling on, to understand what's happening right now before a transaction is approved or denied. And then on the transformation side, you need stream processing to compute real-time aggregations, batch processing for historical features, real-time compute for on-the-fly transformations. There's a lot of different requirements there on the compute side. And then you also need offline and online stores, offline for training data and online for real-time feature serving. And the data between those two stores needs to be consistent in order to avoid any skew or inconsistencies that can hurt your model's accuracy. And then on the serving side, you need to be able to do maybe time travel joins to generate accurate training data, retrieval layers and caching for real-time serving. There's real-time compute, like I said, for on-demand features, and your models need to be able to access all of this data, through APIs and get it really quickly for training and serving, as well as other AI use cases you might have as well. But the point here is that it takes a lot of different systems stitched together to really get the data part of ML right. It's really a huge data engineering effort, and that's why we hear many fraud teams spend the majority of their time on this data engineering part rather than working on the actual model development side of things, because they're trying to do these things like maintain data consistency and meet different latency requirements, keep things running reliably. It all really adds up quickly. So to break that down even further, these are some of the data types, the types of data signals that fraud teams typically work with. They can each have distinct freshness and latency requirements. For example, some features need to be pre-computed, like a 30-day transaction pattern or historical fraud rates, because computing complex aggregations like that over large data sets in real time isn't super feasible. While other features do need to be computed in real time, they need to be computed on demand, like during a transaction as it's happening. Models will depend on data that's only available like at inference time. So the key challenge there is that you need infrastructure that can handle computing and combining like all of these different signals while ensuring that training serving consistency at the same time. And we'll talk about when we talk about teams getting these types of systems to production, which we do a lot of times when we're talking to customers, we hear them describe it as kind of two different worlds. In development, data scientists, they're working in notebooks, they're testing ideas with smaller data sets and doing quick experiments. But getting those features, these new features they create and ultimately the systems themselves to production often, involves throwing things over this chasm, over this wall to, an engineer who's maybe on a different team. And that process is very error prone and time consuming because it involves a ton of data engineering work. For instance, you might have these real-time use cases where you need to know what's happening right now. A transaction is going through and you need to know certain details immediately. Think about needing to know where a user is at this exact moment. The really tricky part of that is bringing together that real-time data with all of your historical batch data. It's, that scenario is huge for so many critical features. Like, if somebody's suddenly on the other side of the world making a transaction from where they usually are, that's, a pretty big deal when you're trying to spot fraud. Then there's things like backfilling. When you come up with a new feature or a new idea and you want to try out a new signal, you can't just look forward. You need to look back. You need to see how that feature would have performed in the past. So you need to run it through all of your historical data. And then once you've got, some cool new features built, you've got to actually make them work at scale, keeping everything running reliably, meeting all of your uptime requirements, things like that. So we're calling out, mostly technical challenges to work on here, but there's also a slew of organizational and like knowledge management challenges to work out, like how you keep track of features, reuse them. You're going to want to govern these, valuable features in your organization, ensure they have all the right approvals before they get to a production environment, things like that. So yeah, this is what we talk about when we're talking about this gap is really about data engineering, and we'll illustrate this more as we go through the requirements that we've heard our customers talk about a lot. When they're talking about building or improving their fraud detection systems. And the first one being the ability to iterate and deploy very quickly. As a data scientist, you might start with a hypothesis about a new fraud signal. Like, we could catch more fraud if, by looking at failed login attempts over the last 2 weeks. You test that in a notebook, you get good results, and then you hit the wall. That is productionizing that feature. What worked in pandas or whatever language you use needs to be rewritten for production. And in the languages of those systems, right? So for each iteration cycle, you could coordinate with your engineering teams, which can take weeks or longer when you're trying to stay ahead, though, of evolving fraud patterns. Like these slow iteration cycles can really hurt your ability to respond to new threats. So yeah, we will just kind of highlight all of these challenges here. But yeah, this kind of just recaps what I just said. Moving on to the second requirement is around data quality. Data quality issues are particularly tricky in fraud detection because they can silently degrade your model's performance. For example, if your stream processing isn't handling time windows correctly, your real-time aggregations become inaccurate. Your point-in-time correctness is crucial. If your training data includes information you wouldn't have had at prediction time, your model learns patterns that don't actually exist in production. One of the biggest issues we see is the subtle differences between training and serving feature logic, and we've touched on that a couple of times. And the challenge is these issues often don't show up as errors. Your model just gradually performs worse over time. So yeah, there's a lot of work involved in building that exactly once processing in a system like Flink or Spark Streaming. You've got to do manual point-in-time joins, maintain separate offline online stores, for example, Redis and Postgres. And each new data source that you bring in requires custom pipeline development and monitoring. So that could add up to a lot of time spent trying to meet this core requirement. And then lastly, there's a lot of strict performance requirements in fraud detection. Getting your streaming infrastructure sorry, my clicker's not working. Getting your streaming infrastructure to perform reliably while maintaining low latency takes a significant engineering effort. You've got to run all of this reliably at scale, right? So pulling all of the relevant data signals quickly enough for real-time decisions while also, making sure they're reliable requires it's a lot of careful optimization. And as you scale, storing all of that historical data for training can become pretty expensive. So managing, on top of that, you got to manage auto scaling, all of these kind of operational monitoring and things like that, which can add up to a lot of overhead and extra costs. That's not necessarily necessary. So let's talk about what fraud teams, what we think fraud teams really need, which is a streamlined way to work with data for ML. How can we make this whole process of productionizing data for fraud detection a lot smoother? We talked about iteration and the need for to test new features quickly. Data scientists and ML engineers need to be able to define features across real-time streaming, batch data, all in a consistent way. They need to be able to try out new signals, validate them quickly. So that's kind of the experimentation side of things. But second, they need to, when it's time to productionize, teams need to have a smooth path to production. Instead of spending weeks or months building out the data pipelines that they need, they want to be able to ship their code and have the data materialization happen automatically. And then the third thing is governance. This becomes crucial as you scale. Teams need to centralize all of their features and get control over what can become a sprawling pipeline environment without good governance. So, and also it can reduce duplication across teams if teams can discover or reuse features. And then finally, there's the serving side of things. You need to be able to serve all these features reliably, like I said, with the right freshness at the right throughput and latency for both training and inference. So serving infrastructure needs to be able to handle everything from batch features to real-time computed features seamlessly. So that leads me to Tecton and what we've built. We are built to help you build, manage, and operate data pipelines for real-time machine learning. The platform plugs into all of your existing data sources, so batch systems, streaming platforms, real-time services, things like that. We are the layer that organizes and handles all of your future infrastructure. So on one side, data scientists can extract point-in-time correct training data sets and test new features really quickly. On the other side, your production applications get the best possible features for inference at the right latency and in a really reliable way. So everything runs on the same infrastructure with really strong guarantees around data quality and correctness. So this is how that kind of looks with Tekton. Features are created, productionized, and managed as code through a declarative framework. And how this works is you write your feature logic in a simple Python file. You can write your transformations in SQL or Spark, Python code. You include some simple metadata like owner, the access controls, production settings, like how do you want this feature to look in production. And Tekton does basically the rest. From this definition, it'll build an end-to-end production pipeline for that feature. We provision all of the infrastructure. We set up the right tables and schemas and configure all of the components that you need. So the result is a really unified pipeline that handles everything from data ingestion to transformation to serving. So your features are always available both for training and real-time inference, all running at production scale. So that's really what I wanted to share with you guys today. Just some context for what Sergio is about to show you, which is a lot more detail about how all of this works. And I'm going to hand it off to him now.
Thanks, Julia. All right, so let me share my screen. And let me start by setting the stage. All right, so this is the Tekton UI. For now, I'm just going to show you that there's nothing here, right? There says no features applied. And I'm going to run and apply. So I'm not going to discuss it right now. I'm just going to start it because it takes a few minutes. And let me talk about how everything is built now. So let me finish setting the stage by talking about our demo scenario. So in this demo scenario, we're talking about a fictitious company called My Wallet, based on most of our customers that do this kind of fraud detection. My Wallet processes mobile digital payments. They process millions of transactions a day, and like many payment providers, they deal with transaction fraud, which causes financial losses and damages customer trust, like Julie has been talking about. My Wallet, in this scenario, starts with data scientists training those models, designing features from the training data they have available, usually from data lakes or data warehouses. They design features, they train their models, and machine learning engineers deploy those models into an online inference platform that also typically includes rules engines that together approve or deny transactions. Now, in order to feed that online fraud detection logic, data engineers need to build streaming transformations to calculate recent activity within each account. They need to establish a baseline of user behavior by using batch calculations of large transaction histories. And they need to build real-time logic to calculate those real-time transactions based on the new transaction and based on external or internal APIs like a fraud score from a fraud service. At My Wallet, like in many of our customers, they built in-house solutions, and they end up using some heavyweight data processing infrastructure. They use things like Flink to do streaming calculations. They use things like Spark or Snowflake to build batch transformations, and they build the real-time logic in Java or Python. And these pipelines are built to produce the same features that the data scientists designed, but they're a different code base. So they tend to have subtle differences in how they're calculated, and that affects model accuracy. And that leads us to the top three challenges that fraud detection teams deal with. They deal with model accuracy, which directly affects their ability to stop fraud, so that affects them financially. It affects customer trust, especially with false positives that deny their legitimate transactions and hurt the customer happiness. like Julia talked about, the iteration speed is a problem because fraud vectors are changing all the time, and taking months to deploy new features and new models doesn't allow these teams to catch up to new fraud threats. And the other challenge is scale and cost. Managing such large transformations and large numbers of transactions and throughput is costly. And developing the pipelines and managing the infrastructure also has a high cost. So with Tecton, things look a little different, right? The data scientist can use a standardized feature engineering language to process streaming, batch, and real-time data to calculate their features and test them from a notebook environment. And then Tecton manages everything else. It manages the data pipeline infrastructure. It keeps the online and offline stores in sync and consistent. And it provides serving of online features for the fraud detection logic, including real-time feature calculations, and provides that consistent training data for model development and model retraining. So with that, let me jump over to the actual demo. Let's get out of the Tecton Apply here. So this is a notebook environment that a data scientist normally uses. And first, let's talk about the transaction history and how to establish that baseline of customer behavior. So this means taking years of transactions for each user and calculating things like how they spend by different kinds of merchants, how much money they spend, so the amount and the distribution of those amounts, and the changes of their spending patterns over time based on seasonality and based on trends. So with Tecton, creating such batch transformations is very easy. So here we start with a batch source of transactions in this environment that the data scientist can still use to explore the data. And here we see the source data. It's the user, the time of the transaction, the merchant location, and the amount of those transactions. The transformation definition itself is it's very simple to define these kinds of aggregations by just listing out which aggregates you want. Each aggregation is an aggregate function. It uses a field that it's going to aggregate, and we're aggregating on the amount here, and the time window that it's aggregating. So we're calculating means over the last day, over the last 7 days, over the last 30 days, and you could use even broader time frames like lifetime aggregations. You could build time series to do the seasonality calculations over this weekly over 2 years, as in this example. And that's all you need to do. So Tecton manages the rest just by setting online equal to true. It will maintain the fresh features, the ones that are going to be served fresh. It maintains the offline store with a history of these transformations for training. You just supply the time horizon for the backfill, how often you want to run, and that's it. You don't need to do anything else. The data scientist can test directly from the notebook the transformations that they defined. So as they're designing features, they can test them, see the results, and these results are calculated in the backfill with a period of validity, which becomes important later as we talk about generating time-consistent training data. They can also define streaming aggregations. In fraud, streaming is important because you need to recognize the most recent activity. You need to know what's happened up to the last known transaction in order to process the new transaction. So you need to calculate sequential behaviors and things like the speed, the number of transactions that are occurring in the last minute, in the last hour, last day, how that spend velocity is changing with the new transaction, what the geographic locations are being used in those transactions, and how that's changing, whether the IP address and the device that you're using is changing. So typically, processing streams requires data engineers to build a process that consumes from a stream platform like Kafka to feed the online store and feed those fresh features. And they build batch processing and different code base to then process those features in batch, the history of those features as it's being built into the offline store to use for training. And this creates a problem of inconsistency between the online and offline stores, because although the differences may be subtle, there are differences in the streaming processing and in the batch processing. Tekton takes a different approach. Tekton uses stream configurations that incorporate both the stream and the batch with a single code base to process both the streams and the batch processing, such that the online features that are being served and the offline history are calculated exactly the same way from the stream data. And it correctly addresses also late arriving data events that arrive out of order into the stream. It's not always easy to deal with. So in Tekton, you define it with the stream source, you define the stream configuration and the batch configuration. In this case, we're using a push config. This allows us to demo and to test live transactions. So I'll be doing that in a minute. And also process the history of the transactions with a batch configuration from any batch storage source. So this is an example of some velocity calculations in a stream in a streaming calculation. As you can see, the aggregation definitions are exactly the same as in batch. So it's the same language, whether you're doing batch or streaming, and the data scientist can define it directly. They define the aggregate, and the only difference, the aggregations are the same as in batch. So, it's the function, the field, and the time window, but you see the time windows are smaller. It's minutes, hours, or 24 hours, or maybe even the last time series for the last few days, last few minutes, or last few hours to detect those transaction patterns that are indicative of fraud. And things like the locations and the span of locations over the last few transactions over the most recent activity. And again, you don't have to do anything else. That's it. So Tekton manages the online offline stores, manages the backfill even from a stream, and manages keeping those up to date automatically. Now, Tekton's engine is the aggregation engine is particularly good at generating ultra fresh features, whether they're batch or streaming, and it does so in a very cost efficient way, regardless of how big the time windows are. From minute to lifetime aggregations, that it can include millions of events and still serve them in under 5 milliseconds. The way Tekton accomplished this is by ingesting the data either from stream or batch and calculating partial aggregations that we call tiles. These partial aggregations are then combined at read time to read less data and still provide all those different time windows in less than 5 milliseconds. These tiles are kept up to date, and in the streaming case, raw events are also added so that you can calculate up to the last transaction in those recent time windows. Again, you can test the streaming logic directly in the notebook, so data scientists can do this as they're designing their features, and they can see how the backfill results are going to be calculated, and they could also test the stream live. So let's go ahead and test it live. So here we're connecting directly to the platform using an API key and retrieving the stream so that we can push new data into it, retrieving the feature view so that we can see the calculations as soon as we've ingested data. So let me go ahead and ingest some data. So what I'm ingesting here is a few transactions over the last 24 hours. $10, 23 hours ago, $100, 10 hours ago, $1,000, 5 minutes ago, and $1 just now. So now let's go ahead and read those features off the online. And we can see the calculations here. I'm just going to point at a few. You see that in the last hour, there's 1,001, the last minute 1, and in the last 24 hours, 11. So now I'm going to show you an out of sequence event, right? So this is 20 hours ago. We've already loaded, 23, a span over the last 24 hours. So this is an event that's out of order, and we're going to recalculate the features with it. So let me point again at in the last hour, because it's 20 hours ago, in the last hour, nothing's changed. In the last minute, nothing's changed, but in the last 24 hours, the feature has changed. So Tecton correctly deals with out of sequence events and updates the features that correspond to those windows correctly. And this is important for model accuracy. Now, fraud is detected in real time, right? So in real time, some features need to be calculated that compare the new transaction with the historic behavior and with recent activity in order to calculate the features that provide the most critical signals to detect fraud. So things like an amount acceleration is calculated from the new transaction amount and the average over the last 24 hours that comes from the stream. Determining whether that amount is an outlier for this particular user depends on batch features that over the last 30 days calculates the distribution as a mean and a standard deviation. So again, in Tecton makes this really easy to define. The new data coming in from the new transaction is defined as a request source, which just specifies the fields that are coming in. Go ahead and define that. And the feature view itself provides the sources. So you provide the transaction, the new data that's coming in, and any other pipelines that you want. The streaming pipeline that we defined, the batch pipeline that we defined, and there's another batch pipeline here that I've included. The attributes that, or the features that you're going to calculate are listed, and then the code itself is receives the inputs as different dictionaries, where this one is the transaction, and these provide the dictionary of values for the features for the particular user that's involved in this real-time calculation. And it does so for all of these inputs, such that you can use just Python code to calculate in any way you want the features that you're building in real time, like the amount acceleration, the distance from the area of activity for this transaction compared to the most recent transactions, whether it's an outlier or not, and whether it's a new merchant. And then finally return them as a dictionary, and that's it. That's the definition of a real-time calculation. The really interesting part is how Tecton integrates all of the different pipelines and provides the calculation on the fly. So an application sends a request to get the features from this real-time calculation that's deployed on Tecton's serving infrastructure. It provides a specific user for this and the new transaction for those calculations. Tecton retrieves from the online store the latest features from batch and streaming feature views or transformations, and combines them with the transaction request using the code you just saw above, and finally returns those results. So Tecton takes care of all of the integration work that's needed, and you don't need to worry about it. You just provide the inputs and do the calculation. So you focus on the logic and not on the deployment infrastructure. So let's go ahead and test this. So again, we're connecting to the platform, retrieving the feature view for real-time calculations, and I'm using that same user that I just created recent activity for, so I can evaluate transactions directly and see the calculations of those features. At 100, the acceleration is low. This merchant is away a certain distance from, and it's a new merchant, but it's not an outlier. Right now, if I calculate a larger amount, you'll see that it changes the calculation. So again, the data scientist can test the real-time calculations and define how those real-time calculations are going to be done. And Tecton takes care of the rest. And like I showed you at the beginning, I did a Tecton apply command. This is the output from that Tecton apply. Let me show you one thing. So the data scientist works using the SDK within notebooks to define the features, test them, and once they're ready to deploy them, they share them with the rest of the team, with the data engineers and the ML engineers, and in a feature repository where they store just those pieces of code that are the sources, the features, and the feature services, which I'll talk about in a second. The Tecton apply command then validates all the code, validates the dependencies among them, runs any unit tests defined in the code, and creates a plan for applying it to the platform. It creates all of the backfill jobs that are needed to create history for new pipelines. In this case, we just applied everything from scratch, so it's going to create all of the backfills, and it's going to schedule the recurring jobs that are needed to keep the online and offline store up to date. So let's go take a look at that UI again. And let me refresh. And you can see now that all of those pipelines are deployed. So in the time that we've been talking, actually in less than the time that we've been talking, all of that code that I've shown you was deployed into the platform, and it's feeding the offline and online stores. It's from this environment, you can see all of the batch transformations that are deployed, the streaming transformations that are deployed, the real-time transformations, and quickly by hovering over it, you can see the data lineage and the dependencies. Data scientists producing new models can come to this environment and find which features already exist. They can look at the individual definitions of those pipelines, see what features are being calculated, and view the actual definitions of those time windows, of those aggregations, and even any other transformations that they include in the code. So with this, data scientists can see what's available, and this promotes reuse as well. So going back to the overall flow here, we also have a fraud detection, the feature services, in this case called fraud detection feature service, that I haven't talked about, so I'm going to talk about that next. But before I go there, ML ops engineers can also use this platform to monitor the compute, monitor the jobs that are executing, to see serving and how the serving latencies for all of those calculations, and they can control access to this data among the users of the platform. So let me go back now and show you the rest of it. So feature services is that last component of a pipeline that defines which features are being used to create training data sets or to serve for inference online. And the way that they're defined is by, let me go ahead and do this, is by defining a feature service that includes, you give it a name, that's what we saw in the UI, and you just list the sets of feature definitions that you want to include. It's going to build a feature vector that includes all of the features calculated in each of these pipelines. So in order to create training data, you need some training events. In this case, we're taking the transaction data and labels of that data to label them as 0 if it's the transaction is not fraud, and 1 if it is fraud, and we want to train a model with this. But we need all of those features that we've calculated. So you can use a get features for events API from the feature service to get Tecton to process your events by using the user ID and the timestamp to do time-aligned joins with the offline store. This means that we're getting the feature values from the offline store as they were calculated at the time of this transaction. So we get time-consistent features that are then used to combine with the other transaction information, with the real-time information, to calculate the real-time features and put that all together with your label with all the features. This can be calculated directly in the local environment, but fraud data sets tend to be quite large, and so normally they're executed in remote data set jobs. This is an asynchronous job where you can specify what compute to use to run the job. Oh, I forgot to change the name. It needs to be unique, so hold on a sec. There's no demo without a little error. So anyway, this just launched a new job using this compute to run it. And you can monitor the jobs directly from here, listing the jobs, seeing what the state of the job is here, and even further monitoring in a monitoring environment through a link. Once it's done, you can get the data set and convert it either to pandas or Spark data frames to process for training, like data scientists normally would do to create their XGBoost model or any other model they want to build. The same feature service is used for serving. So at the serving time, the application or the fraud detection logic submits a request for features by providing the user the context, the user ID, and that transaction information. Tecton does key value lookups from the online store to retrieve fresh features, do those final aggregations from the partials, apply the real-time logic, and ultimately build that feature vector for serving. So let's go ahead and test that. This is the same user I used before to create recent activity. Now I'm going to test the full feature vector creation. And there you go. So I've sent it the user I want, the transaction information, and I get the online features directly for all of the feature views involved, the request time calculations, the batch calculations, and the streaming calculations with the latest values for all features. So with that, let me go back to the setting and just close out here by saying a few things. So I've shown you how with Tecton you can affect model accuracy because Tecton provides point-in-time correct training data. It ensures online-offline data consistency by using the same code base as the data scientist uses for training to actually calculate the pipelines, whether they're stream, batch, or real-time. So there's no online-offline consistency. They can schedule the generation of training data sets and therefore retrain models often and to avoid that model drift. And it handles the out-of-order events like I showed you, so it calculates those features correctly as soon as it gets the data. You can iterate a lot faster with Tecton. You just saw how the simple code definitions were deployed into a production environment. Data scientists can use code that they're used to, right? They code in Python and Spark and in SQL. They can quickly define, test, and backfill data, and it's that single command I showed you to deploy. And from a scale and cost perspective, Tecton is architected for high cost efficiency. Its engines, like the aggregation engine, guarantees reliability, and it provides the serving infrastructure and the real-time calculations to serve high throughputs of over 100,000 queries per second while still retrieving with very low latency. So with that, I will send it back to Julia. Let me stop sharing. And the floor is yours, Julia.
All right, thank you, Sergio. Let me go back to sharing. Okay. Yeah, so to wrap up here, I'm going to share, a concrete example. I want to tell you a little bit about North's story. North is one of our customers. You might know them as North American Bank Card, formerly. They are one of the more prominent privately held payment card processors in North America, and they focus on providing card services to merchants. I actually had the opportunity to chat with North's VP of Engineering and ML Ops recently in another one of our webinars. You can go find that on available on demand if you want, if you're interested. But I want to give you some highlights of their journey today because it's really relevant to everything that we've talked about. So what was North dealing with? Speed and scale were a huge challenge for them. They handle millions of transactions every day, and they've got to make decisions in under a second. Every millisecond really matters for them because they've got customers waiting, and their merchants have customers waiting at checkout. So there's a lot of data that they need to bring together. They're getting, real-time transaction streams. They've got historical profiles on customers, device intelligence data, et cetera, et cetera. All of this needs to come together really quickly. On the engineering side, they were spending months building custom pipelines, working across Flink, Spark, all of these different serving layers. It was just a lot to maintain. And like a lot of teams, they were running into that training serving skew problem that we've talked a lot about. And it was really hard also to experiment with new features. but here's how things changed. When we started working with them, we started digging into these issues with them. And instead of the hard-coded pipelines that they were building across different, with different languages across different frameworks, they were they moved to a declarative approach, like the one that Sergio just demonstrated. That really sped up their iteration cycles and made it so much easier for data scientists to experiment and iterate quickly, because now they've got one unified way to handle batch streaming, real-time data, really consolidated their data processing. So where before they were spending days like manually calculating training data, that's all automated now with all the proper point in time correctness just baked in. But like I said, one of the most important things for their team that they told me is that the data scientists can now work independently using Python and SQL instead of waiting on engineering resources in order to experiment with new features, which is huge for them. And these are some of the outcomes that they achieved. They, cut down on their iteration time. They went from taking months to kind of add new features to models and get new features to production to now just doing it in, weeks or days. They've got their, features consistent between training and production, which is great for, it not only solves a massive like headache, but, ultimately it means their models can be more accurate, which is the ultimate goal. And they can handle different transaction volumes without over provisioning, which saves costs. And they finally got this really historical accurate training data. Their VP of engineering actually said this made their predictions a lot more accurate. So that's what this is all about. So yeah, I wanted to share that story real quick, but finally, I know you probably have a lot of questions about, how this might work for you and your, specific situation, your team. We've got a couple of, great ways to get in touch with us and continue the conversation. We're doing some roundtables with our CEO and our chief product officer next month. And, these will be really, really great opportunities to, learn about different, these challenges in more technical detail, but also share like insights and best practices, network with other, people facing the same challenges as you are. And yeah, we'd really love to have you participate in one of these. So if you scan that QR code on the left, you can register your interest in that and just let us know if you are interested in, in-person meetup or, if you would like to join virtually, that's available too. And then the other opportunity that you have to kind of get in touch with us is if you want, you can sit down with Kevin, our CTO. And this would not be a, Tecton sales pitch at all. It's just a technical discussion about, what he's seen work across different companies. He's done a ton of these, evaluations with fraud teams. So he'd be happy to sit and talk with you about your specific, your specific requirements and situation. So scan that QR code and you can book some time with Kevin. I will also share these links out in the chat window, so feel free to grab them that way as well. But yeah, with that, I'll have Sergio come back up and we can go through some of the questions. I know we got a lot of great questions in the chat that came in, so I want to make sure we have a couple minutes to answer those.
All right, so let me go through the questions I see here that are not answered yet. Isaac has been helping us answer a bunch of them. There's one that says, what's the latency SLA for this service? We are, I believe, at 5.9, so 99.999 serving uptime. The Let me see, how best to organize a call? Well, how best to organize a call is use the QR codes that you have in front of you to organize the call. Does Tecton also provide the rules engine? No. So just to make it very clear, Tecton covers the data portion, right? So everything from data sources to their transformations, maintaining the online and offline storage, and providing the training data sets and the online serving of those features. Typically, this is integrated with other serving platforms like SageMaker for model serving, where it's integrated to retrieve the features from Tecton and run the model inference and the rules engine logic elsewhere in your application. Let me see what other questions are not answered. Okay, you could shoot. Oh, let me see at the top here we have. In the fraud example, the number of transactions in the last 24 hours. Okay. So Isaac has just answered for me, so that helps. So he says, whether the number of transactions in the last 24 hours, do that feature value update if there are no new transactions in the last 24 hours? It should be 0 in that case. And the answer is yes. And Tecton will update the feature values to drop out the aggregation time window and create that 0 value in that situation. I see. I wanted to learn more about how Tecton works. How can I reach out? You can reach out through either one of those QR codes, or if you want, you can reach out directly to me. Here, let me put my email address right there, and I will forward you to the correct person. Or if I can deal with it, I'll deal with it myself. So there you go. Let's see, how about observability and feedback loops? Isaac, do you mind taking that question on observability and feedback loops? So I'm sorry, I'm asking Isaac to come on stage and answer the observability and feedback loop. So he's coming on. Thank you.
So, Drew, sorry, can you repeat that question?
So there's a question about how about observability and feedback loops, and I'm just not sure what they're referring to.
Yeah, so Tecton works to kind of look at 2 different components. One is we're going to always be feature logging. So this is going to allow you to build out kind of feature drift and model drift monitoring capabilities within leveraging either Tecton or other kind of third-party tools for that feature drift monitoring. And we're also going to make sure that we're ensuring that your training and your serving data are always going to be consistent. So we offer both kind of system monitoring as well as some of your other data science observability components like feature drift, as well as ensuring there's no skew between your online and your training data.
Thank you, Isaac. I don't see any other new questions. I've seen multiple. Oh, there's one more. Thanks for the demo. Very insightful. Well, thank you for the kudos. There's questions about whether the webinar is recorded. Just so everyone knows, it is recorded, and all attendees will get a recording. So I think with that, we'll close it out. And thank you all very much for listening to us.
Yeah, thank you so much. Hope to hear from you soon.